Hello, and welcome to the coronavirus edition of ECS 723. Obviously, it's not a good situation, but we'll try to do the best and hopefully make some headway the rest of the semester with respect to educating you and learning about microwave engineering. So I'm going to try to put these together into a movie, and of course we have the electronic version that's already online. This is my attempt. I've never really tried to do this quite before, so bear with me. There may be some rough patches here and there. All right, so let's start with the transformations on the complex gamma plane. And of course, we've been talking about the gamma plane, complex gamma plane, and plotting specific values of loads of gamma L, reflection or short circuits and open circuits, matched loads at the center of the complex gamma plane. And then we went through and we plotted values of gamma reflection coefficient that had certain characteristics mathematically, perhaps their magnitude all equal to 1. Of course, that formed the unit circle. And then other plots on the complex gamma plane for different values of gamma. Where the complex gamma plane really comes in use for us in microwave engineering is when we consider it with respect to the terminated transmission line. So in the terminated transmission line, of course, we know that the line impedance will change as a function of our index Z. As we go from the end of the line, where the load is, back to the beginning of the line, where the input impedance is, we see that that line impedance function will change. Now, there are a couple of points where we know the value of this line impedance function. At the end of the line, where the load is, the line impedance function must be equal to the load impedance. As we migrate back up to the line to the beginning, we find if we evaluate the line impedance there at the beginning of the line, we get a value which we define as the input impedance. And it is the input impedance of that one-port device, a two-port lossless transmission line when terminated by a load ZL. So the line impedance at the beginning of the line is equal to the input impedance. Now we have the same thing if we instead consider the reflection coefficient function. And remember, the reflection coefficient gamma and the line impedance function Z are duals of each other. We have a transformation that for any value of gamma we can determine line impedance or impedance Z and vice versa. And so it's no surprise that once again we have a reflection coefficient function then that will change as a function of position, and we know what that function is. For a terminated line, that function depends on gamma L, the load reflection coefficient. If we go through and we evaluate this reflection coefficient function at the very end of the line, where the load is, then we know by boundary condition that the load reflection coefficient at that point must be specifically equal to the numeric value of gamma L. If we then migrate from the end of the line back to the beginning, the index Z will decrease, have a lower value as we move back toward the beginning. At the very beginning of the line, we can evaluate this reflection coefficient function, and we get a value of gamma, which again we define as gamma in. Just like the line impedance function at the beginning of the line was defined as input impedance, the reflection coefficient function at the beginning of the line is going to be defined as the input reflection coefficient. So we want to know about the relationship between these two things, gamma in and Z in. Of course, we know that gamma L, load reflection coefficient, and ZL, load impedance, are related by the load reflection coefficient definition. We might then wonder whether gamma in is likewise related to Z in, the input impedance, in the same way. And so, are they related in the same form? Well, we know that the line reflection coefficient and the line impedance rather, and the line impedance function and the reflection coefficient function are related by a mathematical statement. Likewise, we could express the line impedance function in terms of the reflection coefficient function. And what that says is for any point on the transmission line, the line reflection coefficient and the line impedance, or the reflection coefficient function rather, the line impedance, are related by this expression. And of course that is true at the very end of the line where our load is. And from this expression we get the definition of our load reflection coefficient. And of course that means that is true also at the beginning of the line. If we evaluate this expression, this mathematical expression at the beginning of the line, we find that the impedance, line impedance, at the beginning of the line, of course, is equal to the input impedance, and therefore the input reflection coefficient and the input impedance are related in the same form as the load reflection coefficient and the load impedance. Again, this is simply, these two statements at the bottom are simply specific cases of the more general statement mathematically that we have at the top of this page. All right, let's go back and look at our load reflection coefficient. It's a complex number. Of course, it has a real part and imaginary part, but also it has a magnitude and a phase, given it being a complex number. And we can express that complex value, gamma L, in terms specifically of its magnitude and of its phase. Given this, we can insert this into the reflection coefficient function for a terminated transmission line and write the reflection coefficient function in this form, explicitly in terms of the magnitude of gamma L and likewise in terms of the phase of gamma L. If then we take that reflection coefficient function and we evaluate it at the beginning of the line to determine the input reflection coefficient, we find we get the expression at the bottom. And this expression at the bottom of the page shows the input reflection coefficient in terms of the magnitude of gamma L and likewise the phase of gamma L. Notice also its value depends on another term, a phase term, which is minus 2 beta times line length L, or minus twice the electrical length. So if we evaluate this expression, we see that the magnitude of the input reflection coefficient is equal to the magnitude of the load reflection coefficient. And of course that's no surprise, because the reflection coefficient function is in fact the magnitude, the reflection coefficient function rather, is in fact a constant with respect to position, constant with respect to the index. So as we move up and down the line, the magnitude of the reflection coefficient does not change. What does change, of course, is the phase of that reflection coefficient function. For example, the input reflection coefficient function is equal to the load reflection coefficient minus twice the electrical length beta L. And so we can rewrite this expression and say that the difference between the load reflection coefficient function and the input reflection coefficient function then is equal to 2 beta L. Now, beta is a positive value, L is going to be a positive value, so this expression says that the phase of the load is always going to be numerically larger than the phase of the input reflection coefficient. As we move from the load, sorry, I gotta get used to working in a mirror image here, from the load back to the input, what we find is the phase value will decrease. The phase of the reflection coefficient is proportional to 2 beta z. So as z decreases, which happens when we move away from the load, then the phase of the reflection coefficient will decrease, which is why the difference in phase from the reflection coefficient of the load and the reflection coefficient at the input, the difference in that phase is 2 beta L, twice the electrical length, a positive value. So the phase changes as we move from the load to the load position to the input of the line, but the magnitude remains unchanged. Now, of course, magnitude of the reflection coefficient and the phase of the reflection coefficient are important parameters when we're plotting on the complex gamma plane. And of course, what we're doing is using polar coordinates, as we've seen before. We plot a point of gamma on the complex gamma plane. Its magnitude is numerically equal to the distance between the origin to that point. Likewise, the phase of that complex value is simply equal to the rotation angle, where we go through and we take from the positive real axis and we rotate in this direction. We rotate, therefore, in a counterclockwise position, the value of theta. Again, a polar plot, the magnitude phase, if we express as a polar representation on the complex gamma plane, provides us the exact location on the complex gamma plane of a specific value of gamma. So, we went through and we looked at a transformation from gamma L back to gamma N, gamma N. We can express this graphically on the complex gamma plane, and this is where the complex gamma plane again becomes very useful to us with respect to microwave engineering. What we're going to do is plot how gamma changes as we move from the end of the line, where the load is, back to the beginning of the line at gamma N. So here is such a plot. Excuse me. All right, so the complex gamma plane has the usual artifacts that we recognize. The horizontal axis is the real axis of the complex gamma plane. The vertical axis is, of course, the imaginary axis of the complex gamma plane. If we were to plot every value of gamma, whose magnitude is equal to 1, it would form the unit circle, a circle with the radius of 1. And of course, that forms the purple circle that we see plotted here. All right, let's say we pick some arbitrary value of gamma L, just an arbitrary point that's within the validity region of the complex gamma plane, a point inside the unit circle. So we'll pick this point here, just at random, has a certain magnitude and a certain phase. Let's say we go through now and determine what is the input reflection coefficient for that load reflection coefficient. And if the, again, transmission line is some arbitrary length, what we'll find is that the input reflection coefficient is going to be, say, this value here. Now, this value, gamma N, and the value of gamma L are related to each other in that their magnitudes are precisely the same. The phases, though, are different, which is why they're different points on the complex plane. We start with some phase associated with gamma L, and it's just some random number. We'll call it theta L here, which is sane in this case. But what we do know, then, is for a given value of theta L, the load reflection coefficient angle, phase angle, that the input reflection coefficient phase angle will be a value which is precisely twice the electrical length of the transmission line, 2 beta L less than theta L. In other words, theta N, the reflection coefficient of the input, is going to be a value of theta L minus 2 beta L. It's going to be less. And of course, if the phase is less, that means we get there by rotating now in a direction which is clockwise as we move along the reflection, the complex gamma plane. The phase will decrease, which means we're moving clockwise. Now, what about the other values of the reflection coefficient? Not the value of the reflection coefficient function at the end of the line where the load is, not the reflection coefficient function at the beginning of the line where we've defined gamma N, but instead the reflection coefficient function at each and every value of index z from the end of the line to the beginning. Well, we know that the magnitude of those values of gamma are going to be the same, both at the beginning and at the end. The magnitude does not change. And so if we plot all those points, we know what we're doing is essentially striking a circular arc. Every point on this red contour has the same distance from the origin. Every point corresponds to a value of gamma, which with the same value of magnitude. What is changing, of course, as we move along this circular arc, this red contour, is the phase angle. The phase angle is changing now from a value of gamma L over here, and as we move toward the input, it's rotating clockwise. The phase is changing, becoming less and less as we move up the line toward the input, until finally, when we get to the input, we have a value of gamma in. This is what we call a parametric plot, this red contour, a parametric plot of the reflection coefficient function. As the index z changes, the value of gamma on the complex gamma plane changes. In this case, providing a very simple contour, a circular arc whose arc angle is equal to 2 beta L. So this is a summary of what I just said. The reflection coefficient at the end of the line at the load is equal to gamma L. The reflection coefficient at the beginning of the line is what we define as gamma in. The magnitude of those are the same. In fact, the magnitude of the reflection coefficient is a constant at every location, index location z. And the phase decreases from a value, original value of theta L at the load, to a value of theta L minus 2 beta L, twice the electrical length at the input of the line. Thus, the parametric plot of this reflection coefficient function, parametric with respect to index z, is simply a circular arc, this should be arc, with radius, which radius equal to the magnitude of gamma L, and an arc angle, arc width, of 2 beta L radians. With this knowledge, it turns out we can easily solve many interesting transmission line problems graphically using the complex gamma plane. So let's do an example here. So let's say we have a transmission line whose electrical length is, or I should say physical length, is lambda over 8. It is 1/8 of a wavelength. And let's say it's terminated at the end with a short circuit. And of course we know the load reflection coefficient of a short circuit is -1, a real part of -1 and an imaginary part of 0. Or we can think of this as a complex number with a magnitude of 1 and a phase of pi, 180 degrees. All right, let's see if we can go through and determine the input reflection coefficient for this particular circuit. How might we do this? Well, here's one way of doing it. We go to the complex gamma plane and we locate the gamma L associated with a short circuit. And here it is right on the left side of the complex gamma plane at a point where the real part is equal to -1 and the imaginary part is 0, or again the magnitude is 1 and the phase then is 180 degrees or pi radians when we rotate around. All right, we start there, and now we're going to strike a circular arc. We're on the unit circle. We're a distance of 1 away from the origin, and so we strike an arc which has a radius of 1, and we simply now rotate around a distance, or an angle, I should say, of pi over 2 radians, 90 degrees. Why is that? Well, because the length of our transmission line is lambda over 8. The electrical length is pi over 4, and therefore twice the electrical length is pi over 2, 90 degrees. So we start at this point where the short circuit is, and we rotate now moving clockwise as we move from the end of the line back to the beginning. Again, the phase angle is decreasing. That's why we're moving clockwise. And we rotate 90 degrees and we stop. When we stop, we're right up here at the very top. A value of gamma, which is numerically equal to J, a magnitude of 1 and a phase of pi over 2. We also know this to be the value of gamma associated with an impedance, which is the inductive matched impedance, JZ0. Now, does any of this surprise us? it shouldn't surprise us because we found out earlier that the value of a 8th wavelength stub had transformed a short circuit into an input impedance, which is the inductive matched impedance of JZ0. And that inductive matched impedance, JZ0, had a reflection coefficient of J. So we know this should be the case. If we go back and look at our circuit, we knew what the input impedance would be, and therefore we would know what the input reflection coefficient would be. And in fact, that's the situation that we had. All right, now let's try something slightly different. Instead of having a transmission line of an 1/8 of a wavelength, let's try a transmission line which has length lambda over 4, again terminated in a short circuit. The question is, what is the input reflection coefficient? Well, one way we could determine this is graphically. We could go on the complex gamma plane, we locate the load reflection coefficient of the complex gamma plane, and then we strike a circular arc. We begin to rotate, again, clockwise rather. The phase is decreasing, striking a circular arc with a radius of 1. But instead of rotating to 90 degrees and stop, like we did before, we're going to rotate all the way over 180 degrees. Why is that? Well, 180 degrees is equal to 2 beta L. For a lambda over 4 length transmission line, we find the electrical length is pi over 2, and therefore, of course, twice that would be pi radians, 180 degrees. We simply rotate around to the other side of the unit circle, and we stop. But of course, at the other side of the unit circle, we find a value of gamma, which is equal to 1. A real part of 1 and an imaginary part of 0, a magnitude of 1 or a phase of 0. And of course we know that is the reflection coefficient value of an open circuit. We start with a short circuit at the end of the line, the load, and when we go back a quarter wavelength, we find that the input reflection coefficient is that of an open circuit. We've transformed a short circuit into an open circuit. Now, is this a surprise to us? Hopefully it's not a surprise. Because remember, lambda over 4 was one of the special cases. It's one that transforms the impedance to an input impedance, which is inversely proportional to the load impedance. And we found, therefore, it transforms a short circuit into an open circuit. A short circuit load becomes an open circuit input impedance. And of course, an open circuit impedance has a value of gamma, which is equal to 1. An open circuit. And that's what we just found graphically, what we already knew to be true from one of our special cases. A quarter wavelength transmission line transforms a short into an open. All right, let's try something different. Let's go through and terminate our quarter wavelength transmission line in an open circuit. So the load now is an open circuit. Its gamma is a value of 1 plus J0, or a magnitude of 1 and a phase of 0. So we're going to start at this point, and we're going to move back up the line to figure out what the value of gamma in should be. Well, again, when we do that, we are rotating around a circular arc and rotating in a clockwise direction. Again, theta is decreasing as we move from the load from one end to the input at the other. And because the phase is decreasing, we are rotating now in a clockwise manner. All right? Oops, I'm sorry. For you, it would be this way, clockwise manner. And again, this is a very important point to get straight in your mind. It's one thing that causes great confusion. Which way are we moving, clockwise or counterclockwise? As we move in the direction of increasing z, the phase increases, which means we're moving counterclockwise. As we move on the line in the direction of decreasing index z, that means the phase value is decreasing, and therefore we are rotating clockwise, around the complex gamma plane. Yeah, clockwise.
I'm waiting!
All right. So in this case, we start out with an open circuit and we rotate around 180 degrees, the electrical length again being pi over 2, 2 beta L being 180 degrees, just like before, but now we end up at a short circuit, a value of gamma n which is equal to -1, a value of gamma n with a magnitude of 1 and a phase of pi. Again, no surprise, this is exactly the what we expect for a quarter wavelength transformer. It transforms an open circuit into a short circuit. All right, now let's take our short circuit, and instead of having a 1/8 wavelength transmission line or a quarter wavelength transmission line, now let's consider a half wavelength transmission line. Again, we start at gamma L is equal to -1 for our short circuit, and now we rotate around a angle that is equal to 2 beta L. Well, if we have a half wavelength transmission line, beta L is equal to pi, and 2 beta L therefore is equal to 2 pi radians, 360 degrees. We started a short circuit and we strike a circular arc that in fact rotates all the way around the circle back to where it started, 180 or 360 degree rotation. And so what we find is that gamma n, in this case, is equal to gamma L. They have the same value. The short circuit at the load becomes a short circuit at the input if the transmission line has a length of lambda over 2. And of course, this is simply one of our special cases. We talked about the fact that if we have a transmission line of lambda over 2, the load impedance will be equal to the input impedance, which means that the load reflection coefficient must be equal to the the input reflection coefficient, and that's what we find in this case. The fact that we started at a short circuit and rotated around 360 degrees is not particularly relevant. We could have started anywhere on the complex gamma plane, and if we have a transmission line length of a lambda over 2, we would rotate all the way around. I'm sorry.
Loser!
I have to get used to speaking in mirror image.
You're a loser!
We rotate all the way around, and we would always come back to the same spot. Gamma n is equal to gamma L. Zn is equal to ZL if, in fact, the transmission line is lambda over 2. All right, let's do a different kind of problem now. First of all, we're going to consider not the load reflection coefficient, but the input reflection coefficient. Let's say we know what the input reflection coefficient is. In this case, we'll try a more general load input reflection coefficient. We'll say it has a magnitude of 0.5 and a phase of 60 degrees. So we know the input reflection coefficient, and we know the transmission line in this case is lambda over 8. The question is, what is the load reflection coefficient? Well, we have different mathematical means of determining this value, given that we know what the reflection coefficient function is. But let's see if we can determine it graphically. So here we're going to locate the value of gamma in our complex gamma plane. Remember, this is the reflection coefficient at the very beginning of the line. And what we're trying to figure out is what is the load reflection coefficient at the end of the line, where our load is. So now we're going to move now up the transmission line toward the input. When we do that, the index z is decreasing, and therefore our phase angle now, oh gosh, I got the whole messed up. Let me try this again.
You fool! You fell victim to one of the classic blunders.
We have input reflection coefficient. I'm trying to think in mirror image. It's not helping. We have the input reflection coefficient, which we know, and we're trying to figure out the load reflection coefficient. So we're starting at the input and we're moving up the line, increasing z as we go toward the load. So in this case, as z is increasing, as we move up toward the load, the angle, therefore, is increasing as well. Now we have a counterclockwise rotation. And so we start at gamma in, and we strike a circular arc, in this case with a radiance of 0.5. That is the magnitude of gamma in. And we rotate a value now of 2 beta L, which is equal to pi over 2, or 90 degrees. Notice I have a typo there. It's not 60 degrees. That angle, 2 beta L, is pi over 2, or 90 degrees. So we rotate counterclockwise from gamma in 90 degrees, and we stop. That is the value of gamma L. It has a magnitude of 0.5 and a phase of 150 degrees, 60 plus 90. Now you might say, why does this matter? We could have done this without graphical interpretation. It's pretty simple. We simply added 90 degrees to 60 degrees to get the final load phase angle of 150. The point is we're in the proper spot on the complex gamma plane. This is the value of gamma L if we were to plot it there. We have the proper location. That may not seem like a very big deal, but we'll find later this is going to be very useful to us for an application.